Okay, so I guess we can get started. Again, hopefully what you're looking at now is just a Jupyter book rendering of the workshop material. And this workshop is going to sort of look at the intersection of deconvolution, GPU computing, and deep learning. So my plan is to maybe go through the material. I'm hoping it'll only take 45 minutes to an hour. And I did schedule 2 hours for this workshop, but hopefully the last hour can just be answering questions, or for people who don't have questions, we can end early. But I'm planning to be around for 2 hours. So the motivation behind this workshop really comes from a lot of the questions that I've seen on the forum about how do we know if AI or deep learning image restoration how can we trust it, basically? And I have a disclaimer here. I am not going to answer that question today, but what I am going to do is I am going to demonstrate the tools that you can use to try to do some more involved experiments that would answer that question. And I also want to emphasize that I don't think the answer to that is black and white. It's not whether we can trust deconvolution or trust deep learning restoration, but it's more of a question of how well does either method sort of generalize, especially for deep learning. How well does deep learning generalize? So if we train it on one type of data, can we trust it if it's applied to slightly different data? And even how do we know what it was trained on, and whether we can apply it to a slightly different type of data? And again, not answering that question, but just demonstrating the tools, some of the tools that could be used to answer that question. And I have a major disclaimer here, which basically the exercises in this workshop are designed so that they could be performed in hours, and some of the networks are trained in minutes. So they're interesting examples, but for real projects, results will be generated like over weeks and months and years. Networks might be trained for hours or days with much larger training sets. And people also are already, I'm using convnets from CARE and Stardist in these examples. And for newer work, they might be using different and more state-of-the-art architectures. So for that reason, some of the results, it's very possible to get much better results, if you put more, basically more time into it. And then a second little waiver here is that, I did get some pretty good results on some of the images, but a lot of the examples of the best deep learning results are sort of like training on one type of, in one domain, and then applying it to basically the same domain in a very, very controlled way. Okay, so the outline of this presentation, we're going to talk about, first of all, installing tools. Then we're going to talk about deconvolution, then deep learning. So hopefully everybody can get to this material online. And the entire first section is on installing tools. So I recently had the privilege of teaching at the Dresden Physics of Life GPU course. And one of the challenges in teaching a course like that, or doing any bioimaging really, is that you're often working with people with very different backgrounds. So for some people, a section on updating, installing tools is material they already know. But for a lot of people, even if they're, good at programming, perhaps they come from like a Java or a C++ background, installing all these Python tools and Python environments and everything is a bit of a chore, and there's like a lot of gotchas that can get in the way. But at the same time, this is really, really important, because if we want to compare, deconvolution with deep learning, we have to, okay, just a quick question. Another person is asking for the link to the Jupyter book, so I'm going to give that again. And again, if you've reached, if you follow the link to the Jupyter book, you should see a screen similar to mine. And to go through the different modules, you just, all the left-hand side of the screen is like a table of contents, and if you click on any of those links, you go to the different sections. So right now we're on course presentation, course preparation. Okay, so a quick word about installing tools. So the best way I have found to create a Python environment for both deconvolution and deep learning is to start from the dev bio using something called dev bio Napari as a base and using MambaForge. So if you've been following Python tool development for the last few years, you probably have noticed that the instructions for all this seem to change like every week. So first people were using PIP, then Conda, then Mamba, and for a lot of us, including myself, who up until 2 years ago, I was mostly doing C++ and Java, all this can be a little confusing. So what I've been doing the last few months is starting with using something called MambaForge, and starting, like most of my environments, using dev bio Napari as the base. And this is, I credit Robert Haas with creating all these instructions and also promoting them a lot on Twitter. So the first chapter of this, or the first section of this course, will give you some instructions on how to install MambaForge and dev bio Napari. And dev bio Napari is going to give you a really nice base. It'll give you Napari and a bunch of extra plugins for Napari. And also, really importantly, it'll also set up some of the libraries that OpenCL needs. So it's going to install something called clij, something called Clesperanto, but that also gives you OpenCL, which we need for GPU computing. So start with MambaForge as the base. MambaForge with dev bio Napari. Then the second part of installing the environment for the course is you need to install several dependencies. You need to install CUDA and cupy, something called TNIA Python, and clij2FFT. So this is TNIA Python is a library that I've made, and it's used, I mostly use it for projections and helper functions. It's really meant to be to aid in like quick prototyping. And clij2FFT is like the clij contains the clij2 version of deconvolution. So that's like an OpenCL based deconvolution. Then also install Stardist and CSB Deep. This will, to get these working with the GPU, you also need TensorFlow. So there's a list of instructions for this. So CSB Deep is a deep learning application, which allows you to do what are called image-to-image transformations, and I'll talk a little bit about that later. Stardist is another derivative of built on CSB Deep, and it's a really nice segmentation deep learning library. And finally, there's another little thing called raster geometry. So if you're trying to get this to work on your own machine, again, go through all these instructions. And then finally, also get the test data. So there is two important little notebooks that you can run after you've installed the tools to make sure everything is working. One of them is called Test Deconvolution Imports, and one of them is called Test Deep Learning Libraries. What I'm going to do now is I'm going to switch. So you should see my screen switching now from the Jupyter book rendering to live code run in Visual Studio Code. So the Jupyter book again doesn't, the web rendering doesn't run live code. So you can run the entire book through like Jupyter if you want, but you could also just run the examples in Visual Studio Code, and that's what I usually use. So this example should work in either case, and it just really goes and tries to import all the libraries, and if it doesn't find a library, it'll say not found. If it finds them, it'll just say found. So this first line says I'm not there, not found, and that's because there is really no library called I'm not there. But the other stuff was found. Then you get the test data, load in the test data, and now I'm running code live, and then make sure you can view it with in a projection view. So what you're looking at here is like a projection of the data in 3 dimensions. And you can also use something called stack view to explore the data. So again, this is a static projection. And I'm just trying to see if the stack view, for some reason, the stack view, I don't know if it's because I'm using webhex or something, but the little stack view widget did not show up, and it usually does. So I'm gonna have to see if that's something to do with the screen sharing. But I will probably add a little bit of information about stack view on the image SC forum discussion, just to clarify what that is and why it's useful. So yeah, so this notebook loads the bars test image and performs a couple of deconvolutions just to make sure everything is working. And then in the end, you can view the data in Nipari. So yeah, so again, if all your setup instructions worked, you should also have an installation of Nipari in this environment. And hopefully you can all see Nipari on my screen now. And the screen looks blank, and that's because by default, the center slice of the image where Nipari opened up didn't have any structure in it. But what we can do here is we can look at a 3D view. We could see here, this is the bars image, that it's just a little test image that we ran just to see if everything was working. And Nipari, I find, is very, very useful for comparing processing algorithms, because you can put them all up, load them all at the same time, and then turn them on and off to see the differences. So what you're looking at, what I just did is I turned off the true image and the 2 deconvolutions. And now what you're looking at is the raw image. And then I can turn the deconvolution back on, and you can quickly see the difference. So you can see in this case, there's been some nice deep blurring here on this image. So throughout this presentation, I'm going to use the Nipari to try to demonstrate differences in image. I think it's just great to see, to very, very quickly see what you've done to the image. Okay, and then there's another little test script here, which just tests to make sure the deep learning part of the installation worked okay. And I don't know how many people are actually running this live. I honestly wouldn't expect, I think all these installations take a while. So I wouldn't necessarily expect people to run it live, but I hope that if you're really interested in getting these tools running, that you take some time later to install them and then report any problems again on the image forum. Okay, so that's the installation section. Again, if you have any questions, please add them to the chat. I'll try to answer short ones in real time. So the next section that we're going to go through is deconvolution. So very quick background on deconvolution. Deconvolution is a procedure that we use to reverse convolution while also considering noise. So in order to do deconvolution, we need something called the point spread function. And in a way, the point spread function can almost be thought of as a simple AI model. And I'll talk a little bit about that relationship in just a couple of notebooks ahead. But the point spread function sort of describes the response of an imaging system to a point of light. And it's basically the basic building block of an image. So images that you take with a microscope aren't built of discrete points. They're built of point spread functions. And then when you have emitters very close together or continuous objects, all the point spread functions sort of blur together and give us the blurred object. I have a quick note here on something called variable point spread function. And I don't want to get too deeply into the weeds here, but I wanted to add this point because in real life, the point spread function varies, and that's a very important part of the problem. So a lot of times in these simulations, we're assuming like a stationary point spread function, and sometimes that's an okay assumption. But in real problems, a lot of times because of aberrations, how light interacts with the real sample, the point spread function is different in different points of your image. So sometimes if you're not getting good deconvolution results, you have to consider that. The next couple of pictures are just sort of a quick example of what happens to an object as it goes through an imaging system. So it gets blurred because of the point spread function. And then there is also noise. So the end result is a blurry and noisy image. And a lot of times the dominant source of noise is the shot noise or the Poisson noise. But and again, in this workshop, that's the only source of noise we're actually considering. So that's another sort of simplification to keep in mind. Interestingly, the other day I saw someone post on the forum a nice summary of all the types of noise that may be in your images. And I'm hoping to, I didn't see anybody has replied to him yet, but I'm hoping to hopefully, again, I'm not I don't have a physics or optics background, so I'm not sure I'm the most qualified to answer his question, but I'm hoping to see some more discussion on that topic, and maybe I'll make a couple of little comments just to bump it, because I think that was a really important topic. But in these examples that I'm giving today, big simplification, I'm only assuming two different types of distortion: the blur from the point spread function and the camera or the shot noise, the photon noise. And then when we do deconvolution, basically we undo the blur. And if there was no noise, deconvolution would be a lot easier. But you see in some examples, if you have a lot of noise in your image, the deconvolution process can enhance the noise. So these deconvolution results are generated with something called Richardson-Lucy, and you've probably heard that term before. It's probably the most commonly used deconvolution algorithm. Most of the commercial implementations are built on it, and that's the algorithm we're going to be looking at today. But one of the problems with Richardson-Lucy is that if there's noise in your image, it'll amplify. It tends to amplify the noise, and that can be a real problem. So then there's some modifications you may have to make to your deconvolution to handle the noise. And then in this little image here shows a noisy result, a noisy deconvolution side by side with one that was constrained with something called total variation to make a smoother result. And that's, I want to emphasize something here. That's perhaps one of the benefits we'll see with deep learning is that maybe it can handle noise better than some of these conventional algorithms. I don't know for sure. I think that's something we should discuss as a community, but from the results I've seen, that's one of the nice benefits. Okay, so that's a quick introduction to deconvolution. So now I'm going to go through some of the deconvolution related notebooks in the workshop. So the first one here is called Forward Modeling. And this notebook is, the audience for this notebook would be anybody who wants to get into the weeds of using GPU FFTs on accessing them through Python and cupy, and sort of looking carefully at how you run them and their memory use, and how you make sure that you are cleaning up all the memory you're using. So the short version of this notebook is it performs a convolution, and convolutions are useful for simulations. I'm not going to get into it too much, but again, the audience here is anybody who's interested in sort of FFT-based calculations and how to clean up memory should take a closer look at this notebook. And we're going to use some of the concepts a couple of notebooks down the line. Okay, so the second notebook in the deconvolution section is one that shows deconvolution of a simulated image of nuclei. And this simulated image was generated by a program called Cytopack. And I don't know if I put a link to that in the slide, but I'll provide a link to that simulator later. So in this notebook, we show a blurry image of nuclei, and we also have the ground truth. So this is a simulation, so it's nice that we have the ground truth. And we then perform Richardson-Lucy deconvolution on this image for a varying number of iterations. So the nice thing about GPU deconvolution is it's really fast. So I've pre-run this block, but you can see here it took about 40 seconds to run. And that did 5 deconvolutions with 20, 50, 100, 200, and 500 iterations. And they're all, it's a relatively small image, but still, they're all done in 40 seconds. And now what I want to show here is a comparison of the deconvolved image and the ground truth. Again, this is a simulation, but here we have a line profile of some structure in the image, and we look at the image, Richardson-Lucy results at varying numbers of iterations, and the truth. So the truth is the purple line. And I could see on this, just let me adjust this a little. Okay, hopefully you can see all the line profiles here. So the truth is the purple line. The image that was acquired was the blue line. And in between them, you could see Richardson-Lucy results at increasing numbers of iterations. And what you should see is that as you run the Richardson-Lucy process, you restore the intensities. You'll never restore them exactly to truth, but you restore them closer to truth. So this is a good little experiment to sort of determine how many Richardson-Lucy iterations I need to get it like a reasonable approximation of the true intensities. A couple of one important caveat is that with a noisy image, you may not be able to run for hundreds of iterations because the noise may amplify before you can actually restore the true or get close to the true values of the signal. Now, something I'd really like to note here is that it took about 500 iterations to really get to really restore the intensities close to the true values. Like I said, we're never going to hit the true values exactly. So another potential really cool thing about deep learning is even if deep learning can't produce way better results, there is the possibility that it could produce faster results. So, and again, you'll see what I'm talking about when we get into the deep learning section, but it took 500 iterations of Richardson-Lucy to sort of, in this case, to get a close to optimal answer. But potentially we could do this with deep learning in like one pass. So it could be used as a way to get faster results or to even accelerate the Richardson-Lucy process. So just keep that in mind. This was a relatively small image, but it took the 500 iterations ran pretty quick on the GPU. But again, with real life data sizes, where you could have images that are like 2048, with thousands of slices and many images, the time, even with GPUs, the time to deconvolve adds up. So the deep learning could be a way to accelerate that. Okay, so the next notebook in the series. The next notebook in this deconvolution series is something called Extract PSF. And again, the audience for this notebook is anybody who wants to try to learn or extract a point spread function from an image of beads. So this notebook, we load a bead image. Then we identify the centroids of the beads. Then we literally run the deconvolution in reverse to get the point spread function. So what is cool about this is it is almost a type of, learning. So by giving the deconvolution system the true location of the beads, we ran it in reverse and learned the PSF. So this is a trick some people use to get the PSF from an image of sub-resolution beads. Okay. Next deconvolution notebook is something that I call deconvolution systems design. So this notebook would be aimed at anybody who wants to experiment with different deconvolution parameters affect the final deconvolution results. And in addition to that, this notebook creates a phantom. It's a pretty simple phantom, just spheres, but it could also be used by tweaking the create phantom block. You could replace it potentially with more sophisticated phantoms, or you could study different configurations of spheres, or just replace this block with you could even potentially generative AI is becoming a big thing. So perhaps in the very near future, we could even use instead of making this relatively simple block, which is just creating spheres, it could be some more realistic sample created by generative AI. One thing I would say about this sphere image is there's a couple of things I've done here to make it a couple of simple things, but just make the test much more informative. So one thing I've done is I've set the intensities of some of the beads to be a little different. So I think the dimmest bead, or the medium bead, is twice as bright as the dim bead, and the bright bead is twice as bright as the middle bead. Just a simple test to see if my results are keeping linear relationship between different intensities. Second thing, so you can notice this sample, as it's configured right now, is the beads on the corner and the bead in the middle are the same size. But with a very slight change to this, the bead in the middle is now really big. And this is important for both deconvolution and deep learning. For deconvolution, a very large object, especially a very large bright object, will emit a lot of fluorescence, and it will bleed through into surrounding objects. So by putting a very large object inside your simulated sample, you can maybe test how well your deconvolution is working on the very, very large bright objects. For deep learning, it's even more important. So one of the things that I think a lot of people have seen in deep learning that is, concerned some people is that if you have a like a large aggregate of fluorescence that was unexpected, sometimes you end up seeing structure in the large aggregate when it's not there, right? So in this case, putting this very large object in the simulated image is a good test to see how the system, to see whether the system is going to put phantom structure in like a large aggregate, which can, I've seen this kind of thing appear in a lot of real images where the structure was supposed to be small emitters or small objects, and just for some reason an unexpected large object gets in the image and gives an unexpected result. So yeah, so in this notebook, we one interesting thing we do is we run the we use 2 point spread functions. We use what I call a forward PSF and a deconvolution PSF. And I think in the current configuration, they're the same, but this would allow you to test, like, if you never know what the point spread function is with absolute certainty. So by making the point spread function that leads to the simulated image different than the point spread function you're using for deconvolution, you could test how imperfections in your estimate of the PSF affect the final result. So again, in this simulation, we apply a forward model. So that's blur and Poisson noise, shot noise. And then we then deconvolve the image. And you see something here called defined number of chunks. So that's important because with real image sizes, a lot of times you can't do the whole thing, especially with the GPU. You can't do it in one block. So you use some sort of chunker or block divider to do the deconvolution in pieces. And in this case, I use Dask to do a chunked deconvolution. For my little simulation, it's kind of overkill because my simulation runs actually on most GPUs without a problem, but it's just there so you can test like the effect of chunking. And so in this example, we deconvolve in chunks and we try a few different things. In this case, I've generated 3 different deconvolutions using different numbers of iterations and different regularization factors, which sort of controls the noise. And then we get a set of different results. There's some code here to look at errors and to look at how segmentation results turn up. But then the interesting thing is we also do line profiles for our phantom, our truth, and our deconvolution results. So you can see, similar to the ones I showed for the nuclei, these are 3 beads, and you could see that the intensities increase, and I did that intentionally. Again, I want to check to see if I'm retaining like the relative relationship between intensities after applying processing. And yeah, so here we have the purple is the truth, the blue is the imaging, and the orange, green, and red are different restorations. you could see that the green one is much less noisy than the red one. These are two high iteration deconvolutions where the true value of the intensities was almost restored to the true values, but the red one is much noisier than the green one. So the green one is when we use this total variation noise reduction, and that works really well on sort of denoising large like regular objects, but then again, like anything, there might be some unexpected effects on very small close together objects. The regularization itself may make the contrast between small objects an issue. So again, the testing of this kind of thing is sort of massively complicated. So here my test is pretty simple. These things are really far apart, but if I wanted to make the test better, I could make some of the emitters closer together to see how features very close together are handled. And again, this notebook is sort of designed so that if myself or anybody else wants to, we could go back up and we could pretty easily change the original test object to contain some like point emitters or smaller emitters closer together. And so then again, this is the same plot, except this is done in the axial direction. And then let's see what happens if we try to view in Nipari. Okay. Okay, so again, this is Nipari is just brilliant for like doing these kind of comparisons, because I just love like turning on and off the different images and very quickly seeing the differences between them. One interesting thing here is that I messed up a tiny bit because I was playing around with this phantom here, and I accidentally left the big sphere in, but I had pre-run the deconvolutions on the little sphere. So I probably can fix that in close to real time. Just bear with me a second here. Go back up here and change this back to a medium sphere. Hopefully this is, so we get this back, and now hopefully within less than 30 seconds, we're going to get back to our, we're going to get the proper phantom in our Nipari comparison. And I think we have. So again, I was going on about Nipari, how great it is for doing these kind of comparisons. I just love to turn everything off, then one by one, turn it all back on. So this is the phantom that we generated. We can look at it in 3D too. Then we can put the image. So this is after blur and noise corrupts the image. Then we can look at different deconvolutions. So this deconvolution was, I believe, run for only 200 iterations. And this one here for 500. And here are the labels these are labels generated from the original or from the image. So I know a lot of people like to claim that deconvolution improves resolution, and I think that's a little bit of a really nuanced point, because what deconvolution really does is it improves contrast. Thus, if you're looking at a contrast-based definition of resolution, your resolution is improved. But what's really powerful about deconvolution is that it increases contrast and can lead to better measurements. So you can see these spheres measured from the raw image are noisy, they're too long. And then if we measure them from a deconvolution, so if we measure them from the deconvolution, we get much nicer results. But you see, it looks like here there's still a couple of spheres missed, and that's probably just because my segmentation algorithm wasn't really sophisticated enough. I was probably using global thresholds and stuff, which missed some of the small spheres. But I think that That's sort of another interesting point because, again, this presentation is on two things, deconvolution and deep learning. So in the deep learning section, we'll see some examples on how to train a deep learning system for segmentation. And maybe you could probably solve this problem where you're missing some of the dim objects by like super optimizing your segmenter code, or maybe you could solve it with deep learning by training deep learning systems to get. I mean, these are little things that either way shouldn't be missed. Okay, so that is the end of the deconvolution section. And again, any questions, please add them to ImageSC or add them in the chat. Okay, so now deep learning. Here. There it is, open preview. Sorry, I was just looking for the preview mode to open this markdown file in Visual Studio Code. So previous to this, I hope some people attended it. We had a great presentation on deep learning for dummies, and it explained all about convolutional neural networks. Very nice explanations, but just a quick review. Deep learning is a type of machine learning sort of loosely inspired by biological neural networks, but it uses sort of like layers of artificial networks to perform a task. And one subset of deep learning is something called convolutional neural networks. And that is a neural network made of what we call convolution layers. So what these networks do is they apply convolution filters to your image, and they actually create multiple different representations of the image or different channels. Then downsampling is performed, and you then apply more convolutional layers. So you're essentially transforming your image from like a high resolution, low channel representation to a high channel. So you're going from a high resolution, low channel to a high number of channels or number of signals, low resolution representation. And this is popular convolutional neural network architecture is called the UNet. This is a picture of the UNet architecture. Yeah, so you transform it from high resolution, low channels to low resolution, high number of channels. Then you transform it back to a high resolution, low channel representation again. However, you train it to find a relationship between the input and the output as to perform some sort of task you're interested in. So the typical types of tasks in deep learning for image analysis are instant segmentation, which is when you want to segment, divide your images into different objects. Semantic segmentation, which is when you want to, it's somewhat similar to instant segmentation, except you want to, instead of just dividing it into objects, you want to identify like what each of those objects are. So you identify sort of pixels as belonging to one of several pre-existing classes. And then there's something called image-to-image transformation, which is when you want to transfer an image from one domain to another. And that includes like image restoration, image denoising, super resolution. So like image restoration, you might want to transfer your image from a blurry image to a crisp image. Denoising from a noisy image to a unnoisy image. And then super resolution from low resolution to high resolution. And then there's an obvious relationship here between image-to-image transformation, deep learning, and deconvolution, because they're both attempting to do a similar type of transformation, which is transfer your image from a blurry, noisy image to a not blurry and clean image. Then there's also, again, a relationship between instance segmentation and deconvolution. So we deconvolve not only to get like images that look better to a human, but to perform a task, to perform science, to perform research. So oftentimes we deconvolve images and we hope that leads to better measurements and some type of better scientific conclusions. So if we do this with classical image processing, we might deconvolve the image, then apply like a classical segmentation and counting pipeline. However, if we use instance segmentation and we train an instance segmentation deep learning network on a set of blurry, noisy images and ask it to produce measurements or objects from that, then we've kind of combined like the deconvolution and the segmentation step into one neural network. And CSB Deep with CARE and Stardist are designed to do that. So CARE is a nice library that makes it easy to do it, to train deep neural networks, convolutional neural nets for image-to-image transformations. And Stardist is a really nice library that allows you to train for instance segmentation under some constraints of that your objects are what we call, or what they call star convex. So it's really designed. It doesn't find like irregular objects, but it's really good for finding sort of roundish or objects that can be described by like a star convex criteria. And of course, for our simulations of things like beads, that assumption will be true. Okay, so that's the introduction to deep learning. So now the next notebook is called training data. And this notebook would be aimed at anybody who wants to create their own training sets using simulations. So what this notebook does is it creates a PSF for the simulation. Then it loads a set of ground truths. So in this case, the ground truths are spheres. And actually, in this notebook, in another configuration of the notebook, it actually loads the ground truths. But I think in this notebook, it's actually generating like random sets of spheres, applying the image system to them. And then you have nice pairs of noisy, blurry images and crisp images, or ground truths images that you can use for deep learning training. And then I have a second little variation on this, which is actually same thing, except it's loading images of nuclei from a set of phantoms that were pre-generated. So it takes these ground truths and generates fuzzy images again to give a training set. So for the examples in this workshop, we have like two types of structure. We have spheres, which is pretty simple type of structure, and we have nuclei, a little more sophisticated. Okay, so the next notebook is called Restore Trivial. And this notebook would be aimed at anybody who would like to take a deeper dive into TensorFlow and how to design like their own neural network architectures. So what this does is it uses like, instead of using like the CARE or the Stardist as like high-level wrappers, it uses TensorFlow to create like a low-level, very simple neural network. And in this case, we totally expect this neural network to fail because it's a totally trivial network with like just a couple of convolution filters and only one layer. So it doesn't have enough like levels to encode multi-resolution information, and it doesn't have like enough free parameters to really do much. But it's just, you know, here's an example of how to start building your own neural networks. And if you wanted to, anybody who is like really inspired could probably take this notebook and expand it to create more sophisticated, to cook up more sophisticated networks. So just there as an example of why trivial neural networks don't work that well and why we need this deep learning architecture. And secondly, just like the skeleton code to start building your own network. But this next notebook, though, shows how to train a CARE convolution net to try to restore our images. So remember, CARE, I probably forgot to tell you what CARE stands for: content aware restoration. And we want to use this to learn basically how to undo the blurring and the noise in our images. So this notebook loads the set of images we created in the 2 previous notebooks. Then there's some steps here that are a little interesting. One of them is that this notebook is set up to use multiple data sources. So instead of I think it might be pretty common to have data from multiple sources. So you might do a simulation, you might label a few images, you might try to take match sets of images using different like sometimes people try to take wide field images and confocal images and try to do image to image transformations between them. So and then you could also, even if you're just doing simulations, you can also have images with different types of structure. You could have images from different instruments or different that were generated using different optical parameters. And an interesting question is, do you need to train these neural networks on both content and optical parameters that are very similar between the training set and the set you want to apply the network to, or can they generalize? So what if you had 2 different, you're taking images, say the simple case is maybe you're taking images with different pixel sizes, and can you train your network to have good performance on different pixel sizes? Maybe. I don't know for sure. What if you had different lenses with different numerical apertures? Can you train a network to handle both? Again, I don't know for sure, but this is sort of an example of how you would look at that problem. So you would want to write a notebook that combined training data from different sources and see how well combined networks can generalize as compared to networks that were just trained for one very specific domain. So yeah, so this notebook actually does the training. It sets up a CARE network. Again, it's probably, if you're interested, study it further on your own, but it creates a CARE network, does the training, and comes up with a deep learning model. In this next network, we actually apply the model that we learned in the first one. So this is called restore. And I'm going to do something here. So I've been demonstrating several notebooks using the GPU for deconvolution. And what can happen is sometimes GPU resources get taken up if you're doing deconvolutions or running deep learning on different notebooks. So sometimes you have to actually restart the kernel to make sure the GPU resources are free. And this notebook doesn't really take too long to run, so no problem starting it. So what I just did is I loaded in a test set of images. So this test set are images of similar nature to the ones I trained on, but I did not include them in the training set. So the neural network has never seen these before. So it's an image of some nuclei, an image of spheres, and a second image of spheres. And I think I wonder if I messed up a little bit because you can see that I think, let me just see this. Let me just run this cell again. Yeah, okay. Give me, I promise, 30 seconds to fix this little slight little issue. So I think what I somehow did is I overwrote my big sphere image, live presentations, right? So I promise 30 seconds. So I'm going to redo this guy, apply this model. Okay. And now saving the correct image, let's go back to our restore and see if we get, so we get this. Yes, so now we've got the correct test set. So hopefully these two little hiccups have actually shown the power of like doing all this stuff on the GPU, because you're able to recover. If the calculations are fast, you're able to recover from little mistakes like really quickly. So yes, this is the test set that I wanted. I wanted the one sphere image with a big sphere in the middle and one with a little sphere in the middle. And this is to sort of test what I call the phenomena of seeing like phantoms appear within large structures. So you want to see if that's happening in your test case or not. So basically, now I'm going to load. So I've pre-trained some models, one called Cytopack, which is trained on just nuclei, one called Spheres, which is just trained on spheres, and one called Combined. And now I am applying them. So I'm applying these models on 3 images. So actually, in this case, I'm only applying the spheres model because I just loaded the spheres model. So loading the spheres model and applying it to 3 images. And what is really cool here, see the execution time? 9 seconds to apply the deep learning restoration to the 3 images. And I think some similar, the Richardson-Lucy for the same images, sort of the 500 iterations to get the really good results, might be about 45 seconds to a minute for the same image set. So yeah, so one potential advantage of deep learning is it may be faster than a high iterative deconvolution. And now let's take a look at the results. So here we go. Here are the results of the deep learning. This was a sphere model. So if we look at sort of the orthogonal view of the nuclei, the sphere model, and this is expected, it didn't do too good on the nuclei, but then it did a little better, obviously on the spheres. It was trained for spheres. It does quite well on the smaller spheres. With the larger sphere, still has a little trouble. There's a little phantom sort of irregular structure appearing around the sphere. And that may be because I didn't train, maybe I didn't train the model on enough examples of large spheres. So that's something I'd have to go back and look at. But it works quite well on the small spheres. And then see if we can take a look at this in Nipari. Okay, so here we go. Here is our images. Here are our images in Nipari. I'm going to go to the 3D view. So this is the corrupted image. And here's the deconvolution. And here's the deep learning result. And they're actually, they're sort of similar. There may be, actually now that I'm looking at this, there may be like a little shift in the deconvolution result. I'm not sure, I'll have to check that later. So if we take a closer look at some of this, let's increase the contrast just a bit. So if I increase the contrast, you could see that in the deconvolution, there's some noise or some yeah, basically a little bit of noise amplification in the background, but in the deep learning result, it's a much cleaner background. And actually, I don't know if even when looking at the not contrast enhanced image, you can on my screen, I don't know if it comes over Zoom, but you can see the noise in the deconvolution result. But the deep learning result, it's restored the spheres, and it's also done some nice denoising. Now, big disclaimer, this is a network trained on spheres and it can reproduce spheres. But as we've seen, it doesn't handle structure it wasn't trained on too well. So now what we can do is we can switch to the cytopack model, which was trained only on nuclei. So again, this is really cool that on GPUs, applying these networks is super fast. This time it only took 5 seconds. So again, great for like live experiments. And yeah, so this time it does better on the nuclei, but we start to see some weird things happening, especially the small spheres aren't too bad, but in the large spheres, we're starting to see some phantom structure appear. Again, so that's one of the reasons I test with these large spheres, is just to see if that's going to happen or not. Now let's see if we can look in Napari. So now I'm looking at nuclei in Napari. I have the input, the deep learning version, and the deconvolved version. Unfortunately, I didn't set things up, and then the 3D views of these nuclei do look kind of weird. I think in this case, the slice view is a little better. Now, one thing, this is actually an interesting view. This is the axial view of deconvolution. And you can still see in the axial view, still looks a little blurry versus deep learning restoration, and potentially looks a little crisper. Major caveat, this was a network trained on simulated nuclei, and then we restored not any image from this training set, but just an image of very similar structure. Okay, and then the final thing, which is, oh, I got a nice question here. Is this notebook running on laptop or a more powerful machine? So that's a great question. This is currently running on a desktop machine with like an NVIDIA, I think it's a 3090. One of the RTX 3090. It's a 24 gigabyte card, really top of the line gaming card. So the training, both this notebook right now is running on that card, and also I did all the training on that card. However, on my laptop, which has a lesser card, still a sort of a high-end RTX, but with only 6G memory on my laptop, I don't have enough memory for training. And I'd also be kind of worried about really overheating my laptop doing like our training. But for the forward, the application of the neural networks, it works great on my laptop with the with basically a 6G, I think 30, maybe it's the 4060. I can't remember exactly what model, but it's like definitely a lower model. So yeah, so training, really need access to high-end stuff, application, medium and stuff, and possible on laptops if they have a good card. Okay, and this is, and then this final little point I wanted to get to is just a point about looking at the line profiles and the relative intensities of the deep learning. This gets tricky. So anybody who's done a little bit of deep learning knows there's something called normalization. There's different ways to normalize images, but basically neural networks handle values that go between 0 and 1 better. It makes the training converge a little nicer. So almost always inputs to neural networks are sort of normalized. And then the outputs, what you train for is also usually normalized. So your mapping also often goes from a domain of 0 to 1 to another domain of 0 to 1. How do you restore that to like true intensities? And that gets a bit tricky because the network might be doing some like nonlinear things. It might be like you might be losing a lot of noise in background. So you don't. It gets a little tricky to figure out exactly how to like restore to the original intensity. So you see my, in my case, at least, I wasn't able to like get the nice comparisons with the ground truth. But I was able to look at like, let me make sure I'm running the right one here. Okay, I think I had a little, hiccup here, but just give me a second here. This is the risks of doing everything in real time. Okay, here it is. So yeah, so I think I didn't quite set up these line profiles right. So I'm just gonna skip that. But the point is it's a little trickier than with deconvolution, looking at the sort of the absolute values of the intensities. You can still look at the relative values, and if you really were careful about how you did the normalization and how your network was handling like background and stuff, you could probably convert it to like another space equivalent to the original image intensity space, but it's just a little bit tricky, and I haven't got that quite working for this workshop yet. Okay, so that is CARE, Content Aware Restoration, Image-to-Image Transformation. The final thing I'm going to briefly go over is Stardist. So the other application that you are interested in using deep learning for is probably some type of segmentation. So instance segmentation, Stardist is a library that makes it really easy to train for instance segmentation for like star convex objects. And given our like little sphere simulation, that's something that Stardist should handle like really well. So here, this example shows you how to train Stardist using some of the simulations we've done, and who this network would be aimed for is anybody who wants to like look at retraining Stardist for like a different size or shape of object. So you could potentially do some simulations, create some phantoms with objects of the size you're expecting in your real images, and then use that as a training set to make a Stardist 3D to find those objects. So that's what this example does. Loads a training set. It trains instead of training the CARE, Content Aware Restoration, it trains the Stardist for instance segmentation. And then we have the final notebook is an example of applying like Stardist. So we load the same image set and then apply Stardist. And so first thing, this nuclei image is, it wasn't trained for structure like this, so we don't expect this to be good. We're just looking at it just to see what happens when you put this into a system that wasn't trained for it. So it finds all kinds of fake stuff. But what I will say is I have seen people use this type of test image and train a Stardist model for it, and it can find these, these 5 different nuclei if you train Stardist on this type of structure. Second image is our image with the big sphere in the middle, and it actually, again, doesn't really handle the big sphere too well. And it also is kind of missing some of the little ones. The final one is just the one with the little sphere, and I think it gets everything in this case. Maybe it missed some of the dim ones at the top, I don't know, but it gets all the ones in the middle layer. Now what's interesting here is, okay, it mishandles the big sphere because it wasn't, I'm guessing in my training set, I tried to put some big spheres in, but I need to look at that again and see, maybe I need to put more large spheres. Maybe so when I'm creating the training images, maybe the image size was actually too small. So it only had like, it didn't have complete large spheres. It just had like subsections of large spheres. I don't know. I'm going to have to look at that a little more, but for some reason it's not handling the large spheres. But again, that's something that you should be able to deal with more work, more care on the training set and everything. But what's interesting is in one case, somehow it misses the corner sphere. Even though the corner sphere isn't any different between the two images, it's only the large sphere that's different. It misses the corner sphere when there's a large sphere in the middle. And I think that may have something to do with the normalization. This is another phenomenon that people have seen, is that if there's something in their image that they didn't expect, it can affect results on some part of the image that does have the structure they expected. And for a type of structure that works fine when it's isolated. And one of the reasons for that, there could be multiple reasons, but one of them could be just the normalization, is that when you have a really large bright object, the normalization works out a little bit differently, and you actually miss the little sphere. So if I was to redo this, I would probably really take care that I had big bright spheres and little spheres in the same image for some examples. Now it works pretty well on the smaller spheres here. Okay, and that's, I think that's all the material here. There's a little, what I call a collaborative assignment. And that's like, we're not going to give anybody like a real assignment or mark you or anything, but just some questions that I think are interesting. And maybe some people have some interesting insights to add. If you have any thoughts on any of these questions, feel free to add to the image.sc discussion on this. Yeah, so that's again, this is just, I'm probably going to look at some of these things in a little bit more detail myself in the coming days or weeks. And just a collaborative assignment meant anybody from the community who has any interesting thoughts, I'd love to hear from you, especially on number 5. So number 5 is that if you know of other deep learning and or deconvolution toolkits that can be used to get better or more interesting results on these images, or in general, I'd love to see you post the results, or point me to the toolkits or something, just to see like what the latest state of the art in this is. Especially of interest would be some of the new SAM segment anything models. Okay, I guess that's the presentation, and I will be around for the next 45 minutes if anybody has any questions or any wants any help on anything.